Hello, everybody. Today we're going to talk about multi-processor systems. Okay, so the basic concept is multiprocessing or multi-processor systems. There are different kinds of things that are defined. Okay, so one is called a single user system. Okay, so one is called a single user system. Then you have so what is a single user system? Something like a single user single processing system. Okay, single processing system. It has got only one processor. Okay, so that is why it is called single processor systems. On the single processor systems, you can run single task. Okay, you can run only one task at a time. Okay, at a time you can run only one task. Okay, so the time that is consumed for every instructions that is there, it is going to be done sequentially as one after the other. So you go into single user mode. So single user mode means the single user is using a particular computer or the complete resources of that particular processor and the IO and the shared memory and all the memory that is available in the disk, everything that is available for that particular type of computer. That is called a single user mode. Okay, multi-user mode is three or four of them sharing the same kind of processor. Okay, with multiple users. That is, you can create two or three or more users on different terminals or IO devices, and each of them requesting some kind of task to be performed. Okay, so that is called multitasking or multi-user mode. Okay, so uh, multi-processing mode is a little bit different. Okay, multitasking is one of the thing, and multiprocessing is something to do with, you can spawn up as many number of shell as you want, and each one of them has what is called a thread. Okay, so the thread is the one which is deciding how many number of processes you can run on a processor. So for an ordinary processor like 286 or 8086 or 186, those kind of things, you can just run only one thing. Okay, now we are going into multi-processor systems. Multi-processor systems are quite complex. There are two or more processor, it is called a multi-processor systems. So they use two different types of memory access. Okay, one is shared memory access or individual memory access. So each processor is assigned a separate memory for itself, and it can access that, or it can use a shared memory or a virtual map of a particular memory and then use it. Okay, that is called. So threading is the one which is used for threading is the one, it depends on a number of processes that can run simultaneously on the machine, number of processes that is running currently on the particular machine. Okay, so its threads are a little bit different and cores are different. So Intel Core i9-7980XC is an extension of iCore. Okay, Intel Core has got about 18 cores are there, so 18 processors are there in the system, and it can be a shared memory architecture, or it can be 18 memory space which it can use separately for it access, and number of threads that can be run is 36 threads. 36 thread means 36 process can be run on the 18 cores. Okay, how can you run 36 threads on a 18 core? It is just that each one of the processor is going to take through threads. Okay, it is called a mixing. Okay, it is called a mixing of instructions. Okay, so two instructions, one from each process will be mixed, so that the thing is pipelined kind of thing. Okay, so it is some kind of clock intermingling and then going on, so that it is working at the same. So the single process is running, but it is going to take the first instruction from one of the threads, and it is going to execute that, and the second instruction will be taken to the other process and executed. So it will be one after the other, or sometimes if it is going to wait for one of the things, then it is going to do the first process. If it is going to first process, if it is going first thread or first process is going to wait for some time, then immediately the second thread which is available, it is going to use that as the next process that is running currently on the system. If it is mostly these things are waiting because of bottlenecks in the memory access. Sometimes it might be IO access or something like that. So that is why the threads are 36 threads. This is the latest architecture, and what the clock it is running is base clock is 2.6, almost like 3 gigahertz. 3 gigahertz is something like 10 to the power giga is uh, 10 power 8 or something like, okay, 8 9 no 9 giga is 10 power 8, giga something 10 power 9 cycles per second. So 1 second it will do 9 10 power 9 cycles, which essentially means that it is going to run at high speed within a second. Okay, so number of instructions it can perform is, the clock speed is about 3 gigahertz, means approximately it can do instructions around half of that. Okay, so it will be 1.5 giga instructions per second. Okay, so that is within 1 second you can do approximately about approximately about 1 giga instructions per second. So that is the number of count. So 36 threads means it is going to be a bit slower. So it will be, if it is 1 giga instructions, then it is going to be like 0.5 giga instructions per second. So that is, so in the turbo mode it is going to use around 4.2 gigahertz, which means that it is a kind of single process or single thread mode. It will be 4 gigahertz, which essentially means that it will be 2 giga instructions per second. Okay, and essentially instruction takes about how many things are there. So you have an operand, you have an operator, and you have a instruction set. So there are about 3 bytes which are used for any kind of instruction. So basically it is going to divide by 3. So a single instruction is into 3. Okay, so when you see gigahertz, immediately you have to divide by 3 and then use it. That is the amount of instructions it can do. Okay, so a single instruction, assembly instruction, is like move A to B. Okay, so it is going to use 2 registers A, B, and say R1 to R2. So it is going to move the contents of R1 to R2. Okay, so source to destination. So that is a kind of instruction. So assembly instruction move A to B, then means that move register A to register B, then it is going to move that instruction, and that instruction will be executed within a matter of 1/3 of the total clock speed. This is approximately the thing. Some of them run at half the speed of base clock. Okay, so that is why it might be if it is approximately half the amount of gigahertz that is available. So this is how you calculate how far the instructions will be executed on it. So 36 thread means it is going to do 2 instructions, not simultaneously, but it will be intermingled. So it will take the first process and do the first move, and the second process and it will do the second move. So 2 instructions are there, some kind of counters will be there, and stack pointers and other things will be. So it will do a memory map of the virtual memory or a shared memory or something like that, and it will be using 2 instructions simultaneously in the sense one after the other, but it won't go and push up the stack and other things. It won't wait on the stack or something like that and things like that. So that is why it is doing almost instructions. So it will be half the number of gigahertz of the total instruction thing. So don't think that it is 36 thread means it is powerful. It is not powerful. It is just that it is going to intermingle this thing so that it gains power. So you don't have to wait in the process wait speed. Okay, so that is why it is going to have that kind of thing. Okay, so first thing you have to know what is a core means 18 cores means 18 processors are there. Okay, if you need 18, if you have 18 cores, then 18 processors are there, then 18 processors are going to have 18 shared memory. Okay, 18 shared memory locations, and each 18 shared memory locations are going to be split into 2 because the thread needs space for that. So each of these 18 cores is going to have 18 separate space for that, and each of the separate space is separated into two different categories of shared memory, which is going to be used to run the process. Okay, that is how it uses those kind of. So base clock is something, turbo mode is something, how the things work. This is the kind of basic things what is happening within a multi-processing system. Multi-process systems, to understand these concepts, what is multi-process system, tasking systems and things like that. Say if you go to a store and you want to buy a product, okay, so you have three counters, okay, so the three counters where you can take or check out the thing, or go get into the thing, and you can check out the items or something like that. So if you want to check out items, three counters are there and people are waiting in a queue to check out from the counter for the service. Then it is going to be three processes are doing, so it means three people are working for the same kind of work, which is checking out. Okay, so which is doing some kind of instructions. So the instruction set is somewhat like that. Okay, now as for how these things happen is, what is shared memory of individual shared memory is like individual trays where the things are put in, and each person is separate individual carts where the things are there, and you take the cart to the counter and then give it to them, and each one is doing separate things. Okay, that is why so three people are doing the things faster, and separate counters are there. That is why the things are processed different way. Okay, now if it is shared memory, then a person comes in and he has a huge lump of things, and then what happens, all the three people take part of the thing, and then share the counter and check out the counter, do the billing, and finally all the things are added up and then given back to them. So that is called shared memory architecture. Okay, this is a simple concept. Okay, you don't have to think too much about it. The basic concept of how you go into your counter, how to process a particular queue, is the basic concept of what is a multiprocessing system. You have to have this basic concept, because that is going to help you how to design a BSD processor, multi-threading, multi-system architecture, multi-processor architecture, and other things. Okay, once you don't have these kind of basic ideas, you will be quite confused what is the thing. Okay, so when you talk about 2.6 gigahertz, it means that, okay, this 2.6 gigahertz is going to be for each one of those, how fast the people are going to process each one of those things. Okay, so each individual is going to process at a matter of 3 seconds. Say each one is going to have 3 seconds, 3 seconds, 3 seconds, and all the 3 seconds are parallel. That is why you get it out within 3 seconds, all the things outside. Okay, so three instructions will be running on three different processes. Okay, so the speed will be much higher. So three instructions are performed. In case of 18 cores, it is going to 18 people that are going to process, and you are going to have 18 or so 36 different processors can be done within 3 gigahertz speed, or 3 seconds. Okay, within 3 seconds, 36 items are going to be checked out. Okay, that is the kind of thing that is related to. Okay, so that is the in a turbo mode it's going to be different. Now if you go and look into the Intel core architecture, let's go and look into the Intel core architecture. Okay, so how within a particular system the things look like. Okay, when you go inside the complete processor, the processor is going to look somewhat like this. Okay, so it has got a memory capacity unit, which is going to be like a small kind of building architecture kind of thing will be there. Okay, so the thread, even the thing you are seeing inside is a kind of thing where it is going to store. Okay, store in the sense, this is a diagram of inside the thing, inside a chip. Okay, this is inside the chip where what you are going to see. Okay, how it looks like is like this. Okay, so this when you see a small line there, or the yellow line, or a thick block kind of thing that is going on from one side, and that will be the size of almost like size of nanometer. Nanometer is 10 power minus 9 meters. Okay, which is about uh, 25 times or even 1000 times smaller than your hair. Okay, that is the line that you are seeing. The thick block that you are seeing on the thing it is going to be like that. So these are all connecting wires, okay? Those are called connecting things. They store what is called a charge. The the shape of the things help in something called a capacitor, okay? The shape of a capacitor is at the lower layer, okay? So if you look at the bottom, that is a capacitor of storage, okay? And the top one, if you see, it has got a different kind of structure. That means it is going to have a read cycle and a write cycle. The write cycle will go to the lower one where it is going to be stored in the capacitor cycle, and the read cycle is going to be done on the top where it is going to read from the location and get it out into the processor, okay? The processor also has same kind of architecture, okay? Only thing, it will be a little bit different, okay? When you look at these things, what is the gap in between? What you see some kind of gaps also in between. What are these gaps for? These are all semiconductor gaps, okay? Semiconductor is a kind of element which allows for these gaps to be performed. So if you make a charge on one side, the charge is going to be stored in the capacitor, and that charge is going to be drained, and the storing of a charge is going to be called what is called a 1, and if it is discharges completely, then it is going to be 0, and the gaps that is there in between are the ones which are going to charge the thing and discharge the thing immediately. So when you give a current voltage to something, it is going to charge the capacitor, and then finally if it is going to the top one is going to just read from the what is charged inside, is going to read the thing. So when you give a read command or a write command, say move register, move from location A to location B register, okay? So the move command is going to come in and it is going to read. Move means it is writing, okay? So or you want to copy command or something like that. So this copy command will do only read. So that read is going to come on the top line, and immediately it will read what is there inside and then get out that particular signal or 0 or 1 outside, and that is going to come as the read, okay? For writing, you have to do both the things, one on the top and one on the side also. So these two things, uh, when they are done, then you have a write cycle. So it is first going to drain the thing and put a new kind of charge, whatever charge that is given on the new things, and that is going to store at the bottom of the, it is somewhat like a water pipeline kind of thing which it is going to store, okay? So you have a some kind of cup like structure. It is just for storage of charges. One is a shield for the particular charge, and the inner layer is going to for storing the charge, and the middle thing which is going inside is where the charge, positive charge is given, okay? So the middle thing is going to give a positive charge, and the inner cup is going to store that particular charge, what charges you gave. Because of that, an induced thing into the side, okay? So if you give a plus voltage on the middle one, then it is going to give on the side a negative thing, and the negative charge will be formed, and the negative charge will be stored like that there till the next when you take out the voltage, the negative charge will be still stored because it is a capacitor kind of thing, and the outer thing is a kind of shield for that, so that it is the charge doesn't jump out of the thing and is stored within that particular kind of element, okay? So this is the basic concept of capacitor storage. It's basically for extreme fast memory location like RAM, internal RAMs, external RAMs, and things like that. So this is the kind of architecture that is they use for reading and writing onto. So it's basically some kind of capacitor kind of thing. How the capacitor, they charge and discharge, that's all. These are the two things for a capacitor, okay? They charge and discharge. So memory location is either read or it is return. Return means it is going to charge. If it is discharge means it is going to write, which is going to make it 0. So reading means just going to take the contents of the thing and just give it to the output, that's all, okay? So some kind of gated arrangement will be there so that it comes out of the thing, that's all, okay? So this is the base, how the things looks inside. Even the processor have same kind of things, but it will be a little bit more complicated or something like that, where you have other kinds of control elements that will be coming in, and the space between that is a kind of other kinds of elements that might be used, okay? So The wall like thing is what is it is a it is just a some kind of metal kind of thing, and the outside is called the base. The base is where the it's more like some kind of semiconductor base which will be used on that this small metal things are etched. Okay, so this is the kind of how it is etched and how the charges are. So once you give a voltage, these things are going to be stored, and so these things are extremely small. As I told you, one thousandth of a hair. So this is almost like 1 nanometer, which is the space in between and things like that. Okay, the entire thing will be around, say, about 20 nanometers. What you're seeing here, the entire thing will be around 20 nanometers or 30 nanometers, which is approximately about the size of half the hair or something like that. Okay, that is the kind of thing which is there inside. Okay, so now we go into what is the kind of things that is there inside that whole processor. Okay, there are three different things. One is called CPU, GPU, system cache, context hacks, okay, security, IPU, and BP. Okay, so first thing is some kind of base pointer is available, so that is the kind of things. Okay, so you have a central processing unit, and GPU is how it is used. Okay, so system cache is the one which is going to be the cache. Right now we saw all the things, that is the capacitor kind of thing which is going to be there. That is going to be there in the system cache. Okay, so GPU, and you have security. Security is the sense you have read write cycle, which is kind of security things, and TPU. Okay, terminal processing unit. Okay, those kinds are going to IO kind of thing. So IO kind of thing will be TPU, IPU. Okay, TPU. So in order to access the different kinds of process, so we have three different of processing units: CPU, GPU, TPU. Okay, so these are the, so context hub is the one which is going to do switch between these three depending on what context it comes into. Okay, and the other one is base pointer, ISP. Okay, that is called internet service provider or something like, or IO service provider, internet service provider. So it is a kind of clue. Okay, so let's go. So this is the basic memory architecture and other things. Okay, now we are going into our things. What are our things? What are our things? Our things are going to be like the how to write the multiprocessing system. So last time we saw how the BSD Unix was classified. So this is going into the internals of some of the parser architectures. The base concept is, I told you, queuing, lining, and things like that. Okay, so that is the basic queuing, lining, and other things. Now we are going into what is called now let's go into GNU or something like that and find out where the things are. Okay, documents, GNU, BSD, okay, SRC1. So this is not the one. So we go into what internal storage. Okay, the storage, and you have pictures, recordings. Okay, we have GNU, BSC, SRC. Okay, SRC bin. Okay, then you have to do process wait or PS or process wait pkill. Okay, shell and move and things like that, make direct. So I wanted to show you something about the inode, and I don't know where it kept those things, but still we have to find out where the things are. Alarms, Android, audiobooks, cache, DCIM, document viewer, documents, download GNU, movies, pictures, it's not in there, recordings. Oh, okay, so this is where the thing is. Okay, so this is where the thing is. Okay, so the basic BSD kind of system, Unix kind of system is going to have, in SRC it is going to have countrip, crypto, etc. GNU. GNU is something to do with general network utilities. Okay, it is general network utilities. or general utilities basically. Okay, so GNU is a kind of compiler or for C compiler or something like that. Okay, lib user bin and things like that. Okay, so that is for GNU. Okay, it is provided by GNU. So those kind of things. ETC is the one I told you, extra things that is going to be, that's mostly something to do with configuration of the different hardware, and you have to map that hardware into what is called a file system. Okay, so the basic concept of mapping all the IO devices plus the memory plus the bus plus the processor architecture is all going to be, that configuration information is going to be available in ETC, and extra configurations also are available. What are the so when you are going into multiprocessor system, I told you already about the bin. Bin is the one .exe file. The .exe file is going to have three kinds of blocks. Okay, the first block, it's all zeros and one will be. Okay, if you look at the exe file, it will be all zeros and one, zeros and one, zeros and one, but it is divided into three parts. Okay, the first part will say what is the exe. Okay, this is called a code segment. Okay, the lowest part will be the code segment, and then you have the data segment, and then you have a stack segment. So these are the three things that will be there. As for segment, that segment will be as a memory allocation, it will be done and it will be mapped onto that particular thing, where it will take these three, immediately put it on the processor, load it on the processor and start executing the thing. So it will have a virtual kind of pointers pointing to different locations, where you can, the stack segment will be pointing to the first instruction of the instruction cycle of the code, and it will be pointing to some of the data also. So the stack segment is used to how to manipulate the entire process when it is running. Okay, so each one of those zeros and ones and other things of every 13 or 64 or 32 bytes of bits will be from the code segment will be an instruction. Okay, basically it will be an instruction and followed by some of the arguments and other things. Okay, or it might be register arguments, or it might be memory location kind of arguments and things like that. Okay, so that is how the code segment will be. The code segment, when you see zeros and ones, you can immediately identify what corresponding assembly code will be there. Okay, because say for move instruction, it will be 00100001 up to 32 bits and some kind of 001 at the end, so which means it's an instruction and it is a move instruction. Okay, so that is how the things are there, and following the next extra zeros and one are all where from where to which location. So pointers can be stored, so it might be a pointer, relative pointer. So most of the things are use relative pointer while assembling the things and converting into a binary code. So binary code is 0 7. So if you see the whole thing, it will be a 0 7 1, and three segmentations happens, and you have an extra segment also. When you have multiprocessor systems, you have what is called an extra segment. This extra segment, okay, it's called ESS. Okay, extra stack segment. Okay, that is the one that is used for identifying which kind of processor it is going to run. So you can run it into higher kind of things when extra stack segments. When you do the compilation, it is going to know which kind of processor. If you have a multiprocessor unit, then it is going to have a ESS segment also along with the bin code. So because it is a multiprocessor system, we have to specify the thing, because we are going into a different kind of architecture. Now whether it is useful or not, it is a big thing. Okay, whether you want a single user or you want a multiprocessor system, it doesn't make much of a difference. But what is the thing, it is because multiprocessor systems are close, you are putting 3 or 4 computers into the same thing, but IO resources are different, but the memory and other things can be used immediately and faster. So when you put things closer, it is going to be much faster, the processing. Okay, and you're running on a single clock cycle, so that you don't have to separately do the things. It is like a slow counter and a fast counter. And even if you have a fast counter, if one counter is extremely fast and you're just waiting for so many other things, then it is going to be very difficult. So in order to speeden up the process, you have a single clock coming in and 5 processes taking the same clock and running the whole thing at a much faster speed. So the architecture itself is quite difficult, okay, was for especially building with the GNU Unix processor multiprocessor. Building the Unix multiprocessor system is quite difficult because you have to define all the libraries for that, you have to define all the sweet coding for that, and you have to define what are the targets, and you have to define build all the libraries, special libraries for those, and secondly you have to include the compiler for those things also, separate compiler for multiprocessing, which will allow for multitasking. So you have to create an ESS, extra stack segment, which allows for multiprocessor to specify exactly which processor, and each one of those ESS segment will have which kind of processor. Okay, so if we are running a 8 core processor, it might be numbered as 5. Okay, so 5 for that particular shared memory. That extra stack segment is the one which is used for to do that particular thing. So here you have i386. So this is a 386 processor. So all the individual control elements for that particular process is given here. Okay, so because it is a multiprocessor system, 386 maybe it's a multiprocessor system, so it is having that particular kind of things. Protocols are the ones which are going to use other things. Okay, anyway, that is not needed here. FS tab, FS inode and other things. I wanted to today show what is in types, ISO, kernel environment, language, link, locale. Okay, malloc and calloc. So malloc and calloc is the one which is generally used for memory allocations within that is virtual memory space that is allocated to do some kind of work. So processor basically allocates some kind of space for that particular kind of data structure and starts using those things. Okay, so they are used mostly for memory allocation. And so if you see open something, open file and close file, or init a process, so create and destroy. Okay, so when you if you have a C code where you have some kind of statement like what is the thing, what is the general statement in case of C++. C++ will have what is called a create, and I think it is end or something like that. So that release, okay, something memory release. Okay, so these are the process creation and class definitions coming into existence and just removed out of the memory, so the pointers are coming in. So SIGL will be the one which is used to release the memory. Okay, memory locations and other things. Okay, but I don't have the complete thing, get ops and global.h. So in order to port all these things, you have to understand the BSD systems thoroughly first of all. Okay, or any kind of Unix operating system. Once you have a Unix operating system, you have different kinds of things going on. So you have to do src include source src sys. Okay, sys I think it is include sys include no, sys dts is I wanted to show you the inode and other things, so where you can use the thing. This is net NFS. These are all protocol kind of things when you see all these things. Okay, user src include, where is the include, user src, user src, okay, recordings src sys a b c d e f g h I. Where is the thing? Well, let's go into the thing sometime. Okay, so sys include is the one which is going to be used. So if you do go into the include, okay, I don't know where the thing is, but anyway, so there's some kind of include file will be there. Okay, so gne contribute lib sqs bin. Okay, so okay, it might be in sbin. Okay, sbin sbin init. Okay, so init is the one, and init is the one which is going to do all the things. Okay, Init.c is the main thing which is going to do the process kind of thing. Okay, so if you go into what are the things it is going to use. Okay, it's a param, boot trace, IOCTL. So first thing, input output control structures is going to be used, allocated. Okay, so mount, reboot, status, syscontrol, UIO, wait, and things like that. DB, error number, signal. So all the signals are going to be used. All the path structures are going to be used. Time structures are going to be used. These are the things for usually to sleep tells to process control systems. Okay, getty and other things, static file. So once it is done, the main thing is, this is where the main thing comes in. So it is going to have get PID and other things, RBRC, open log, while init.c. I think this is not the one. Okay, maybe it is somewhere else. Anyway, so let's go into some of the things and then find out what is static void, get current. Okay, this is not the one. I think it is going to the end or something like that, where it might be there available. Init.c. Okay, signals p wait, close, fork. Okay. Run final. Okay, this is run final and it's got a PID fork. So fork is the basic thing of process thing. Okay, so when you do a fork, it is going to create a new process. Okay, in case of Unix operating system, you have to use fork or exec. Okay, so these are the two things that are used in case of Unix. In case of BSD, it is a little bit different. Maybe it's in BSD it is used as fork and exec, and Unix is the other way around, or probably something else. Okay, or SH should be run. Okay, CSH, MSH, and other things will be run. But anyway, so this is the basic kind of things where you are going to look into. So signals are going to be defined for each one of those processors, and signal weight is going to be used for the one of the shared memories and other things, and you are going to do a complete mapping. If it is shared memory kind of architecture for a multiprocessor, then it is going to be, signals are going to be interacted, and each one of those IO for the process is going to be used, and signals are going to be sent. So you have to write separate signal structures for each one of those processes. Sometimes it is single signals of a data structure might be available, where all the 8 processors give you signal depending on which processor is interrupting you. So you have to catch all the signals of the different interrupt processors, and check on the memory location and do a long jump, or kind of switch over. Okay, so that is the basic kind of thing that is going to be used. So how to do the entire thing for a multiprocessing system and other things, it's going to be a little bit more complex, but you have to know how to make all the things. Okay, that's MK node is there. Okay, so this is just an introductory of how, and multiprocessor systems are configured. A little bit on the hardware, a little bit on the kind of architecture within inside, on what those when the hardware means what. Okay, when you say 8 core, 16 core, 32 core, and things like that, and what is the kind of, whether it is shared memory or a single memory, or a multiple memory that is being used for doing different kinds of processing. So these are the basic concepts before you start writing the code for the multiprocessing systems. So only thing is fork will be P4, process 4, where you have different PIDs coming in depending on which processor it is running. So you will have different kind of process ID, and you can sometimes, if it is a single shared memory, then you don't need any kind of single. It will be considered as a kind of single process, but within the shared memory, it is going to distribute on each one of those 8 different kinds of cores. Okay, so that is how it is going to be done. Okay, so in order to write the code, you have to understand the hardware thoroughly. Okay, and what kind of signals they are going to give in, which processor is going to interrupt, how you are going to overthrow the thing, and which kind of shared memory will be used, something like that. Or you might write code which is kind of virtual kind of code, which is not going to, so you have to just, you can treat the entire thing as a kind of single processor kind of thing, and you can just give commands like that, so that within the processor they'll do the sharing of, kind of parallelizing the things and things like that they'll do within the thing. Okay, so there are two different types. One, either the software does individual kind of loading and unloading to each one of those processor and doing all the things, or the software might the software is just kind of hidden out of the processor, so that you have a single kind of interface to the software, so you can just write a software as though you are running a single processor kind of thing. Okay, and processor are going to just run on each one of those things depending on number of threads that is going to be. So threads are the one which are used in kind of as a kind of process command. Okay, so you just call the thread and then assign the thing, okay, to run on a particular kind of uh, system. Okay, so this much is enough for today. So I wanted to show you the actual process thing where you can make changes and other things, but I don't have the IO table and other things, how to define the IO table and other things and do all the things. This is just an introductory. So next lecture maybe you can have other things coming in. So that is all for today about multiprocessing systems, how to port for multiprocessing systems and BSD kernels, BSD or